This video was brought to you by Hexagon. Every rocket launch tells a different story.
Flight directors go for launch.
A story about the people who built it, the machines that shaped it, and the thousands of decisions made long before countdown ever begins.
Minus 10, 9.
Most people know SpaceX for the part of that story we can see. The engines, the launches, the rockets that return to Earth, but that is only the final moment.
8, 7, 6, 5.
Because before Starship ever reaches the pad, another kind of work has to happen. Inside the factory, teams are turning problems into parts, test results into improvements, and individual discoveries into processes that can be repeated.
4, 3, ignition.
I'm Travis Egan with IMTS, and today we're going inside SpaceX to see how they're scaling their manufacturing capabilities for one of the most ambitious engineering projects in history.
Minus 10, 9, 8, 7, 6, 5, 4.
Since the beginning of the space age in 1957, every era has had a vehicle that came to define it. Gemini taught us how to work in space. Apollo carried us to the moon, and the space shuttle changed what an entire generation thought a spacecraft could be. For this generation, Starship has that kind of ambition. At 407 feet tall, it is being designed as a fully reusable transportation system capable of carrying more than 100 metric tons to orbit.
On Starship, the goal of that mission is to recover not only the booster, the first stage, we also want to recover the ship, the second stage. And so all the work that we're doing is navigating all the engineering challenges to accomplish that task.
One version of Starship is being developed with NASA to carry Artemis astronauts from lunar orbit to the surface of the moon and back. And beyond the moon is SpaceX's longer-term goal, carrying people and cargo to Mars. That is an enormous promise, and delivering on it requires more than a remarkable vehicle. It requires an industrial system capable of building, testing, and improving it again and again. Most of Starship's visible story happens at Starbase, Texas, where the vehicle is built, tested, and launched. But more than 1,000 miles west, in Hawthorne, California, another part of that system is taking shape. Hawthorne is where Falcon and Dragon were developed, and it remains an important part of SpaceX's manufacturing operation. Michael Sulgrove, who heads up the Starship components team, wanted to show us more than just the individual parts they manufacture. He wanted to demonstrate how the entire operation fits together as a whole. Because this isn't just a tour of a machine shop, it's a look at everything SpaceX has built around it.
Our team is responsible for designing all the pressurized fluid components and a few of the mechanisms that are on the Starship booster and the Starship ship. So everything from the engines up, all the pressurized fluid components and actuators on those vehicles, our team's responsible for designing them, machining them, assembling them, and testing them, and then completing that whole life cycle for a variety of products that service the Starship mission. Our goal is to have everyone that does the work together, so there's no barriers. By having those folks working together as kind of a smaller team on that product, they can iterate more quickly.
What Michael is describing is common. As a manufacturing process begins to mature, bringing teams together and optimizing the way a product moves through production is to be expected. What makes it unusual here is that Starship and many of the components inside it are still constantly changing. They're optimizing a production system around a vehicle that is still evolving.
All of the components exist for a reason. The system exists for a reason, and the reason is driven by the mission requirement. So what are we trying to do with Starship? Hey, we're trying to recover the ship. All right, well, what are some of the different phases of flight and how does that impact what's necessary from the propulsion system? And then bringing that back into, okay, what would a valve need to do in order to accomplish that task? We take our best shot to make a product. And then, usually we get it a little bit wrong. And so we work with everybody on the team to iterate and come up with a design that is lower cost, more reliable, and higher performance.
I'm really excited. Can we go in and take a look and see how all these things are working in parallel and get a little bit of a behind-the-scenes look?
Yeah, absolutely.
And that's where this story gets unusual. You may already have noticed parts of the image being blurred out in this video. As I'm sure will come to no shock to you, many of the parts that Michael and his team are developing here for Starship cannot be shown. But that gives us a better way into the story. To understand why this shop matters, we do not need to see every detail of a Starship part. We need to understand what a part like this has to do.
This is our assembly area. Here, this is our highest volume product that's on Starship. So we've built that competency to really understand which features matter about each of the piece parts in the valve. And then we've used that to say, hey, if we were able to hit this particular tolerance, we could change the design in this way, which would simplify the valve and make it more reliable and lower cost.
Now, I'm sure some of you watching are wondering what exactly a valve is used for. Here's one example. This is not a Starship valve. It is a gaseous hydrogen flow control valve from NASA's Space Shuttle program, but it helps explain the kind of challenge Michael's team is solving. At its simplest, a valve is a gate inside a rocket's plumbing, and when I say plumbing, I mean that almost literally. This diagram shows the flow paths inside a single Space Shuttle main engine. Fuel and oxidizer move through a network of pumps, pipes, and combustion systems and valves, determine where they can go, how much can pass through, and when that flow has to stop. Each highlighted point represents a different decision the engine has to make: open a path, isolate part of the system, or precisely regulate the flow moving through it. And everyone has to make that decision reliably, under enormous pressure and across extreme changes in temperature.
So it's curious to me, do all valves leak? Is that just inherent in a valve, or can it be completely sealed?
Yeah, we kind of have a running joke, going back as far as Dragon, that everything leaks, even metal. We're dealing with very small molecules for a lot of our pressurized media, and so any sort of cut, imperfection can lead to leakage. And so in this area right here, what we're doing is we're taking the finished product, the valve that's been fully assembled, and we're testing it. So inside of each one of these chambers, we have all of the different pressurized media that replicates what we have on the vehicle, as well as the thermal conditions. So these are cryogenic valves, so we test them at cryogenic temperatures, because at those temperatures, things move and we can determine what the actual leak rate will be on vehicle. And then all of the sensors and equipment that you see on these panels, that's used to replicate all of the types of environments that you might see on the flight vehicle in terms of pressure in every single, orifice, direction, and range.
But valves are not the only challenge Michael's team has to account for. The Space Shuttle also had gimbaling engines, but its 3 liquid-fueled main engines performed one continuous burn during ascent. Starship is designed around a broader cycle. Selected engines must shut down and restart as it stages. Detach, maneuver, return, and land propulsively. Its valves, actuators, and mechanisms must maintain pressure and precise control through movement, vibration, repeated starts, and ultimately, repeated flights. But first, they have to pass the tests here.
So then if it failed, if it had a high leak rate under whatever test, it would be then scrapped, sent back?
Yeah, depending on the leak rate, it would either be torn down and we'd try to find the root cause and then determine why that happened, or we might scrap it depending on the scenario.
All of this testing serves a larger purpose. It is not simply checking whether a valve matches its drawing. It is showing the team whether that drawing produces a valve that can actually perform under the conditions Starship demands. In rocket hardware, details too small to see can carry enormous consequences. During STS-126, part of a hydrogen flow control valve fractured roughly 90 seconds after liftoff. The mission continued safely, but the failure triggered an extensive investigation. It showed how damage too small to see can become consequential under pressure. And inside the cryogenic systems Michael's team is testing, even a tiny variation or trace of debris can matter. That level of scrutiny exposed another problem: time.
We've had issues, especially in development. We're still learning. We're trying to figure out the designs that are going to work. And then also the designs that will allow us to build efficiently and quickly, right?
Sure.
So sometimes we've gotten parts in and maybe they're not exactly within the tolerances that we need, which causes problems during the build, but mostly what I've seen at least is like during the testing phases. And so we'll want to do some redesigns, maybe tweak some of the tolerances or tweak some of the design. When we have them outsourced, it takes a little bit longer, but when we're working with our partners, our teammates here, we can make those quick changes, which allows us to move very quickly, but in a reliable sense.
To keep pace with Starship's growing demand and components that were still evolving, SpaceX began bringing more manufacturing in-house. Outside, suppliers could make the parts, but with tolerances this demanding, the team sometimes ordered multiple sets just to get enough that met requirements, and every handoff slowed the next solution. The goal wasn't simply to make parts themselves. It was to connect manufacturing directly with design, assembly, and test. In 2018, that began with a single machine.
How many machines are in this facility comparatively to 2018?
Yeah, since 2018, we had one machine. Now we have 34 spindles, and the project we're working on now is getting up to about 110 spindles just for this department.
So 110 spindles in the machine shop here for Starship or for?
Just for Starship components. So that's valves, actuators, things that are on the stage side of the booster and the ship. Not the engine, not any of the other systems, just those products.
But scaling meant more than adding machines. Each one introduced another process to supply, monitor, and keep running. So SpaceX began treating the machine shop itself like an engineering problem. The goal was not simply to build more parts. It was to create a connected, increasingly automated manufacturing system capable of identifying problems and keeping production moving. And when Michael showed me around the shop what went into that process of automation, the level of detail was incredible. But not every problem had a ready-made answer. And when the existing technology stopped short of what the operation needed, the team began building the missing pieces itself.
All right, Michael, so we talked a lot about automation today. Can you talk to me about some of the engineering automation that's happening sort of behind the scenes and how it impacts the shop itself?
Yeah, so one of the things we noticed early on in the shop is, like I said earlier, what are some of the things that are consumed on the machine? Tooling is one of the #1 consumers.
Sure.
And so what we put together at the back of all of our machines is a way to label for the operator every single tool that's going to need to be replenished, and we restock right here at the machine, all the consumables.
in the bay.
Yeah, and then the next thing we noticed after that is they were constantly going between the back of the machine and the front of the machine to understand, hey, which tool position is running out, which one do I need to replenish? So we've developed this software that refreshes every time we change out the program. It tells the operator which tool position it needs to be replenished before the machine's going to stop. That means we have enough consumables in our tool crib to run for those 24 days. And it says right here we have 2 days of raw material. The reason for that is there's an upstream operation ahead of this machine that is filling.
That is where SpaceX's work with Sandvik comes in. By managing the tool crib digitally, the team can prepare everything required for an upcoming job before the machine needs it.
And really, one of our goals here is to build a automotive-style production line for tooling. When we finish the expansion, we will probably have in circulation well over 7,000 to 10,000 holders that are being used on a daily basis.
Okay.
And to manage the consistency of all the nuances of every single tool, because any tool built incorrectly can either lead to the part being bad or crash the machine.
Once you begin treating the shop as a connected system, every interruption becomes another engineering problem. That instinct appears throughout the operation.
The machines that we are expanding with, we tried to keep them consistent because that allows us to build that digital environment and all those scenarios much more efficiently here. A lot of the things look similar, but there are subtle differences between the configurations, and managing those configurations is really what makes it pretty challenging to operate. So actually what we just saw over there with the automation, when we're talking about that screen, as well as the tool display, all that uses MT Connect and the Think API to be, that's how
it enables that communication.
Yeah.
The team is constantly looking for ways to understand a process, stabilize it, and eventually automate it. And one of the largest obstacles they face is also one of the most ordinary: a metal chip.
Our main goal here is to try to understand any sort of chip packing or chip issues. Since we're working on a lot of turning operations, what we found is that anytime we have chip wrapping, that limits our ability to automate the process.
Chip packing happens when the metal removed during cutting begins collecting inside the machine instead of clearing away.
And so this is one of the experiments we wanted to run with the engineer. He said, hey, if I can look at my G code and I can look at where we're seeing chip wrapping or chip packing on certain areas, I can work on improving the process before it ever goes in the machine. Yeah. And so we're trying to learn from that here. And it's incredibly important because anytime there is chip packing or chip wrapping, we have to stop the process. Otherwise, we have small imprints and sealing surfaces, which causes us to fail testing later. We're working with, liquid oxygen, liquid methane. When those things mix, obviously that's a bad situation. So any leakage is obviously not great, and this directly impacts that performance.
None of this means SpaceX is trying to build every piece of technology itself. The real decision is determining which capabilities are core to the mission and where an outside partner can bring deeper expertise.
For us, when it comes to machining, we want to be really great at the process of converting a print into a stable process that makes a great part. We would really only ever take on internally if it was like core and critical to our goal. And really our goal is to, manufacture spacecraft at rate. And so a lot of the other things, are not really our core competency or goals. So that's where we work with people. We like to have a deep collaboration, invite people to the shop, make sure they understand where we're going, what we're trying to accomplish, and say, hey, how can we work together to develop this technology? Because, we want to push them to improve their product so that it can improve our product.
And one of those partners provides a crucial step in the manufacturing process, making sure the part was built correctly. And as the operation scales, inspection has to become faster and more connected alongside it.
This is one of our global CMMs. We're looking at generally a 1.2 to 1.7 first micron first term accuracy.
To put that accuracy in perspective, a human hair is roughly 70 microns wide. This hexagon system can measure to within about 1 to 2 microns, roughly 1/30th the width of a human hair. That is the role of metrology, measuring dimensions, surfaces, and geometry at a scale the human eye could never verify on its own. Hexagon's equipment gives the team the data to catch those differences and connect what happened inside the machine back to design, manufacturing, and test. Without that measurement, the feedback loop is incomplete.
So what we're going to do is we're going to touch the part and basically check, make sure the concentricities, coaxialities, datums, flatness, all the things that are called out on the print are done correctly to print so that everything fits.
All of these systems are being developed inside an operation that SpaceX is already preparing to outgrow.
Right now we're standing inside the first floor of what's going to be our expansion. What we're trying to do here is create an environment where all of the machining, design, assembly, and tests are as closely located to each other as possible. So if you look kind of on the second floor here, this is going to be our engineering office. So everyone on the first floor is going to be where we're operating, machining, making the parts, and directly above them, that's where all of our, programmers, engineers, leadership, machine maintenance are going to be sitting and co-located right with the shop floor so that they can understand any issues on the floor and, quickly go and resolve them.
How many additional machines do you think that'll be in this?
Roughly 60 to 70 more machines.
Okay, within a year, essentially.
Within a year.
For all the attention paid to automation, Michael does not describe the future of this operation as a factory without people. The machines can repeat a stable process, but someone still has to discover that process, understand why it fails, and decide what should change next.
And, that's really part of why we're expanding the shop is, once we can get enough smart humans working together and solving these problems, we can accelerate, right? A lot of people that join the SpaceX mission, they're excited about the mission. They're excited about, hey, how do we get humans into space? How do we go to the moon? How do we go to the Mars? For our team, we're looking for people all across the country. Anybody that's just excited about the mission, wants to get results, wants to be pushed. That's kind of what we're looking for.
Earlier in this series, Paragon showed us what happens when critical manufacturing knowledge disappears between generations of spacecraft. Here, SpaceX is facing the next version of that challenge, not recovering the capabilities of the past, but building new ones before the demands of the future arrive. That is what this unfinished facility represents.
Flight directors go for launch.
SpaceX is not only building for the Starship that exists today, it is building the capabilities required for whatever the program encounters tomorrow. And that brings us back to where we began. A launch is the moment everyone sees, but what leaves the pad is the result of every test, every problem discovered, and every solution made repeatable. Starship launches in Texas, but part of what makes the next one possible is being built here in Hawthorne.